Hello.
We are live.
Hi, good evening, everyone, and a very warm welcome. And thank you so much for joining in. We're so glad that you could join us for the third edition of the TECHRx series. This is a collaboration between INC and AMTZ and KHIT, the Kalam Institute of Health Technology. And the goal of the series is to create a dialogue between the scientific fraternity as well as modern day society by instilling and sparking the imagination through innovative conversations. My name is Vipasha, and I work as an idea discoverer at INC. INC, with its decade-long legacy, is a pioneer in accelerating the journey of game changers all across the world. And AMTZ, being the Center for Medical Technology, Innovative Research, as well as incubation of startups, have collaborated to bring together this monthly series of conversations. Today's series is going to be a conversation for 60 minutes, and we will open the last 20 minutes for audience questions as well as people joining us on YouTube. This is being streamed live on InTalks YouTube channel. And please feel free to make it as interactive as possible and keep dropping in your questions. With that, I would like to call upon Lakshmi Pratury to moderate the session. Lakshmi is a business leader, entrepreneur, story curator, and a former VC who's passionate about community building and instilling the innovative DNA in thought leadership. And we have a very, very special guest joining us all the way from Australia, Professor Gordon Wallace. He's an eminent scientist who's internationally recognized for his research on materials for energy and biomedical applications, and was appointed as the Officer of the Order of Australia and also named the NSW Scientist of the Year in 2017. He's currently the Executive Director of the ARC Center for Excellence and the Director for Intelligent Polymer Research Institute, the Australian National Fabrication Facility, and TRICEP, which are all headquartered at the University of Wollongong. With that, I would like to extend a very, very, very warm welcome to the Executive Director of ACS, Professor Gordon Wallace, as well as Lakshmi Pratury, the founder and CEO of INC. May I please request the both of you to turn your camera on, please?
Hello, everyone. This is Lakshmi Pratury. Welcome, Dr. Wallace.
Hi, nice to be here.
Hi. Hi. So I'm just going to give just a very short introduction. So the format today is I'll give the introduction, then Professor Wallace will make a presentation. Then I'll come back and ask a few questions and open it up for everybody to participate. So I just want to say that, this whole TechRx conversations are a sign of what's to come. Corona or no corona, we have moved from a very, very industrial economy to a creative economy. And in this economy, innovation comes from people from very, very different disciplines working together, and also different stakeholders, the government, private enterprise, public enterprise, academics, all of them working together. And AMTZ is a prime example of a space where many, many different people come together. So INC and AMTZ partnered to launch TechRx as a monthly series where we can explore different aspects of science and technology and social good and academia, various aspects. So all I want to say is that today we are exploring an area that's incredibly applicable. There are many scientific rigors, scientific research that we are doing today. Maybe the light of the day can be seen at 10 years or 20 years, and it's extremely important to do the work now. So innovation keeps on. And 3D printing and this coming together of technology and science in a very, very big way has been happening for a while. But the inflection point is now in terms of there are so many applications that are possible in this, and the amount of social good that can come out of it is so huge that the time has come for this subject to be in the mainstream. I have come across this a couple of years ago. We had an INC fellow who has who's been doing 3D printing of skin, and, it was an academic interest, but really what he said made me think is that today, when there are so many burn victims, we are able to supply a very small percentage. And that too, the way we do it is you graft the skin from another part of the body and you put it. So for burn victims, skin is very important. So if we can 3D print skin from your own cells, the kind of social good that can come out of it is really, really huge. So when Alok Medipura, who was one of our Inc. fellows, said this, it really opened my eyes to how far the technology has come, but really how much of social good it can do. And people like Professor Wallace are taking it even tenfold high by combining really cutting edge research that's looking into the future to what is happening today. So, Professor Wallace, with that, we really look forward to learning what's happening in your lab and then later on discuss what are the various implications. With that, we are truly honored and excited to invite Professor Wallace to address us today.
Great. Thank you very much for the kind invitation. And I'll just share my screen. Is that coming through okay?
Yes.
Okay. Look, thank you for those kind words of introduction, and thank you for the opportunity to talk to you this evening here from Australia. It's really an honor to be able to share some thoughts with this audience and to enter into conversation with this audience. As you heard in the introduction, I'm the director of a national centre of excellence that involves all of these universities that you see on the screen. And of course, many of you will know that we've been building our collaborations with AMTZ over recent years. I want to talk today about how 3D printing has acted as a catalyst to enable some technologies to converge, and then how 3D printing has converged with other areas of technology to deliver clinical solutions. I'm going to start with an example which is really quite ambitious. It's a project that we started a number of years ago called the Brain on the Bench project. And it's one of those projects that will be incredibly demanding for 3D printing and bioprinting to achieve. But I want to illustrate that by setting those lofty goals and setting that bold vision, and by collaborating with people along the journey, there's many opportunities to be had that can deliver shorter term impact from 3D printing. So the brain on the just check my slide here. It doesn't seem to want to change. Okay. So the brain on the bench project, like all of our projects, starts with a challenge and an idea to meet that challenge. And some years ago, with these two collaborators, and also with Professor Graham Clark, bionic ear fame, we thought about how we could better communicate with neural systems. That would enable us to have better neural prosthetics, like the bionic ear or a prosthetic hand, for example, that's driven neurally. It would also enable us to build models where we might be able to understand how neural diseases develop and to test interventions for those neural diseases on the bench. As you will know, today, at the moment, we use animal models in order to try to study those types of systems. Those animal models are expensive, the experimentation times are long, and often those animal models are not particularly relevant to the human condition. So there has to be a better way to do this type of research. And knowing what we did about 3D printing and the ability to print different types of cells in 3 dimensions and to strategically arrange those cells into a structure, we thought that perhaps we could start to think about creating a piece of a brain on the bench, which is actually functional. And by building our collaborative network, as I mentioned before, we've been able to identify other spin-offs of that technology that are much more immediately applicable. And that's the story that I want to tell you today. And I think what I've learned from many of our collaborators that we have to dream big and have big vision, but we also have to be determined to deliver. And we have to be determined to deliver for the communities we work for as we strive towards that bigger dream. in order to realize advances like this, there are a number of strategic areas of technology that need to be brought together. One is materials discovery, where we need to take the most advanced materials or the most newly discovered materials that can interact with living systems and be able to fabricate those using advanced fabrication into forms that we can utilize straight away for biological applications. A great example of this is graphene. It was a material discovered not very long ago. It's an amazing material, just single sheets of carbon that have extraordinary electrical conductivity, very high thermal conductivity, and their biological activity can be tuned by the chemistries we can attach to the edges of those sheets. So we've discovered, of course, tens of thousands of new materials in recent years. So, why is graphene so important? Well, it's important because in parallel with the fundamental properties of the material being discovered, we also discovered clever ways to fabricate structures containing graphene, like these micron dimensional fibers here on the right-hand side of the screen. So we've developed some processing technologies that enable us to make fibers the diameter of a human hair with incredible strength, but also incredible flexibility. And what that meant is almost immediately we were able to start animal experiments, implanting these fibers into the brain of animals. When they got in there, the sheath would dissolve, the mechanical sheath that helped take them in. And then it had this flexibility combined with the strength, which gave them incredible durability in animal experiments where we wanted to record signals from the brain. And I mentioned the extraordinary electrical properties before. So the signal to noise ratio we could obtain for these neural firing, these neural activity within that brain was much better than any conventional electrode could achieve. That strength and flexibility enabled us to go into another area of animal experimentation. And that is where we used the fiber where we could tie it in a knot. So we could tie it in a knot and not interfere with its electrical properties. So it was like a suture, which we called a sutrode, because this suture we could tie around very, very fine nerves and record from those nerves and stimulate those nerves. And so we were able to do these types of experiments where we're interrogating the neural system at levels that we could never interrogate before because of advances in materials and advances in fabrication. But as I mentioned before, there's the limitation of animal models, and we will learn and we will pursue this avenue of research, and we will learn a lot from mapping neural activity within animal models. But we really need to have an alternative to this approach to move more quickly and to understand more relevant models as we move forward. Because if we
Dr.
go back to
Wallace,
the bench and we
Dr.
look at
Wallace,
assemblies of living cells, of neural cells, if you look at that in 2 dimensions, as on the left-hand side, and we look at the firing pattern from those neurons that are interconnected, the electrical firing pattern, you see that it looks quite stochastic, it's quite noisy. But as we go to a 3-dimensional structure, so we distribute these cells throughout a gel, you see that you get a pattern within that firing from those different groups of neurons. And that pattern is very much more similar to what you would see in vivo in a living system. So 3 dimensions is important. And in other studies, we found that 3-dimensional biology is important. This is work where we use organic electrodes to stimulate cells that have the characteristics of schizophrenia. So their neurites have died back. The degree of branching or interconnectivity has suffered because of the genes that we've taken out. And we find that if we stimulate those systems in 3 dimensions with a new organic material, we can restore normal activity into those cells. So there's lots of evidence now that we need to be building 3-dimensional models on the bench if we're going to do realistic experimentation and understand how those biological systems work. So we were very fortunate to get engaged in 3D printing almost 2 decades ago. We started to build 3D printers that could print new materials like graphene, that could print biomaterials like chitosan, and also print living cells and build structures up layer by layer with different types of materials and different types of cells integrated into those structures. One of those biomaterials is chitosan. So as we pursued this printing of graphene for neural applications, we used chitosan, a known biomaterial that's compatible with living systems, as a structural component. And this is where, working along the pathway with other clinicians, immediate applications become identified. Because what we found that is that we 3D print just chitosan with our collaborator here, Professor Peter Chung, an orthopedic surgeon, that framework is an excellent framework into which we can introduce adipose or fat stem cells and generate cartilage in a controlled environment. So we've taken the simplest structure you could 3D print, combined it with known advances in stem cell technology, taking fat stem cells, modified the mechanical distribution of our 3D printed structure, and introduced the fat stem cells to get very efficient cartilage regeneration. So this project has accelerated dramatically in recent years. And of course, we're going to reach an endpoint on this before we reach an endpoint on the brain on the bench. We've introduced and developed new inks now that enable us to print those adipose stem cells directly into a structure, and indeed directly into the wound that we're trying to repair, or the defect in the knee that we're trying to repair here. So we've developed new printing technologies to go along with the advances in materials and the advances in stem cell technologies to tackle this area of cartilage regeneration with Professor Peter Chung. Other surgeons haven't seen what we did in the knee, and this is Dr. Payal Mukherjee, who will be known to many of you in the audience there in Vizag. And Payal and I have worked together with AMTZ as part of an Australia-India Research Council grant, where the idea is to grow cartilage in the shape of an ear now, so to build the complexity a little bit. To get a structural material as well as the gel biomaterial to facilitate cartilage regeneration, and to actually print a living ear to treat patients with microtia who are born with a part of the ear or maybe the whole of one ear missing. And we've developed a new printing technology that allows us to do that. Now we print a scaffold in the shape of an ear. We print a gel that can help grow the cartilage. And there's a customized printing technology that allows us to do all of that. And then there's another spin-off from that. Through our collaborations in India, we've discovered, and then subsequently discovered back here in Australia, that there's also a real need for a simple solution to 3D printed prosthetic ears. And so we've been developing a whole system that enables us to use a mobile phone to scan the ear, to slice and dice that information into a simple 3D printer that we've created in order to print prosthetic ears that can be deployed very effectively throughout a widespread community. So this is really a very simple 3D printing solution, but it impacts on a lot of people, as you heard in the introduction already. So we can shoot for the stars with the brain on the bench, and we should and we will, but along the way we shouldn't miss simple opportunities, technologically simple opportunities to deliver real solutions for people in need. And that's what we're doing with each of these projects. So just going back to my first colleagues, Shufeng Huang, who got us interested in the 3D printed brain on the bench in order to understand schizophrenia and how we might treat it. And Mark Cook, also wanting that model to understand the development of epilepsy and how we might treat that. And I've mentioned some of these other collaborators already, Peter Chung and Claudia De Bella in the cartilage, and Payal, cartilage in the ear. And there's others. There's Toby Coates there that we're working on a 3D printing solution for islet cell transplantation. And Professor Fiona Wood, and you heard in the introduction about 3D printed skin, and I'm very familiar with our Look's work. And we've been working in this area with Professor Fiona Wood to develop a printing technology that prints directly into burns, into wounds, in order to facilitate to skin regeneration. So, a simple base technology, advances in materials, advances in fabrication, combined and converged with stem cell technologies, really does deliver a lot of opportunities. But back to our brain on the bench, and where are we? How have we been able to combine those or converge those technologies to advance this longer term project as well? So here's some of our recent work where we were printing neural stem cells using a special ink that we created to ensure viability of those rather delicate cells during printing. And what we were able to show is that after the printing, we could make sure we could differentiate those neural stem cells into different types of neurons. And that's very important because this brain on the bench has to have different types of neurons and also different types of supporting cells arranged in 3 dimensions if they're going to function the way we want them to function on the bench. And we took a step further than that in looking at induced pluripotent stem cells. So these are cells that are taken from an individual, fat stem cells, for example, and then fat cells, and then reprogrammed to stem cells. So these are the individual's own cells. And of course, that opens up some other very exciting possibilities because now what we're doing, we've got this ink where we can print those induced pluripotent stem cells. We can induce differentiation into different types of neurons and supporting cells. So coming back to Mark and Peter, to epilepsy and schizophrenia, what we can do is to take stem cells or cells and reprogram the stem cells from healthy individuals as well as from individuals that have schizophrenia and those that have epilepsy. And we can grow those tissues on the bench and then start to understand how those diseases develop and how we might be able to develop interventions that can fight against the further development of those diseases. So that's required the input of a whole lot of different people with a whole lot of different skills. And where we are now is almost full circle because we can print those scaffolds. Here's our electrodes that were going into the brain before of the animal or being tied around the individual nerves in an animal. And now we can use, this is actually using a silicone rubber printer like the prosthetic ear printer to create structures that have those fibers embedded. And we can start to print our 3D neuronal cultures into that receptacle, and we can study those and start to understand the development of those diseases. So 3D printing really did catalyze the bringing together of materials discoveries with advanced fabrication and stem cell biology. It's brought those fields together. And now what we're doing is combining that technique with years, decades of knowledge in tissue engineering and new emerging knowledge in contactless characterization to enable us to do this tissue reconstruction on the bench. So if we go back to our brain on the bench idea, which really did emerge around the year 2000, it had this rather linear approach that we planned to engage in. But as you've seen, the journey has not been linear. We're still heading towards the brain on the bench. There's been many other opportunities along the way. And the reason that those opportunities have been identified and exploited and delivered on is because of our engagement program, our ability to communicate with a whole lot of different clinicians and other people with other non-technical skills to address ethics, regulatory, and commercial models. And what we've learned in this area of engagement is don't wait to the end of the program to get started. Engage early, engage with others outside the field, engage with those involved in very important issues that will determine the translation into the clinic. Of course, we have a global network, and AMTZ and our other colleagues in India are a very important part of that. That global network serves 2 purposes. One is to accrue the best knowledge from around the world in order to tackle these multidiscipline challenges. But equally important is it's a global technology deployment network. So once we have solved something, we have a network in place where we can deploy that knowledge to the benefit of the maximum number of people possible in the shortest time possible. So we should dare to dream, but we should be determined to deliver. We should work with others because some others may have been around the corners that we're about to go around and may well have knowledge that helps us to plot our journey much more carefully and much more effectively. Collaboration is important in many fields. Collaboration is absolutely critical in this field if we are to realize practical applications. And I'm going to thank you again for the opportunity to join with you this evening. We're excited about this field. We're excited about working with colleagues around the world to deliver in the short, medium, and longer term using 3D printing and associated technologies. Thank you.
Thank you, Professor Wallace. It's truly fascinating. I mean, in some ways, to see where we have come, and especially when you talk about you can take the stem cells, and if you can study a healthy and a schizophrenic mind side by side over years, and you can see exactly what can go wrong when. Is it possible to use that knowledge to go back and change the scenario? I would like to understand from you, once we understand what's the difference, how can we actually apply it to maybe even contain the problem?
Yeah, I think that is certainly the intention. There
Yeah.
are, as I understand it from my colleagues, there are indicators of schizophrenia, for example, in terms of early indicators in terms of cell behavior, that if you can intervene then, you can prevent the full-grown onset of the disease. But of course, that's part of the whole study. And
Correct.
you know,
Yeah. I mean,
you just couldn't do this experiment right 5 years ago,
correct.
and you can't do this
Correct.
experiment in an animal. So
Correct.
while people talk about 3D printing, and I've illustrated it here as well, and many other people do, delivering
Right.
immediate solutions and intermediate solutions right now today, but it's enabling us to do fundamental research that you would just dream about just a handful of years ago.
Exactly. Exactly. I have a clarifying question. You were talking about the electric impulses and like a suture kind of a thing that's wrapped. Is this suture that you're wrapping, does that contain small electric pulses that's sending the information back? What is the way in which this suture is communicating cell information back into the system?
Yes, so it's basically the equivalent of the electrode that was poked into the brain, except that it has such mechanical properties. You can actually tie it around extremely delicate nerves. We're talking about 50 to
Okay.
200 micron nerve bundles here.
Mm.
That example that I just flashed on the screen just showed 4 electrodes tied around individual nerve bundles. They're actually nerves that go into the spleen. They've never been able to be interrogated before. And it turns out that all of the information in those 4 different nerves is very different. And so if you're kind of trying to control what happens in the spleen by electrical impulses, you really need to get down to that level of resolution. And that's what we're starting to do.
Great. I'd love to open it up for questions. And before that, I have one last question to you is, there is a whole ethical questions that come with all this, right? I mean, in the world of designer babies and stuff, 50 years down the line, if I know exactly what causes schizophrenia, I could go back and design in utero to make sure it doesn't happen. I mean, anything is possible. So what are, while you are doing the research as an academic institution, what are the things you are in?
Sorry, I've lost you. Did I try it? Oh, you're back.
Yeah, sorry, we missed you for a second.
Yeah, sorry, I lost you. I think you were asking about the ethical considerations
Correct.
and
How do you
complications.
train your all of you as scientists? How do you the boundaries? What are the things you're thinking of?
Yeah, I caught bits of that, so I'll try and have a go at the answer. Look, within our centre, we have a group of researchers and educators who deal with ethics policy and public engagement. They ask us continuously all the sorts of questions that scientists are not used to being asked, and I think it's a very important part of training of the training program for younger scientists. I think that the scientists of this generation are being equipped with tools that those of us in other generations were not equipped with, in terms of realizing that these are issues that are not to be left to others to solve, that scientists, engineers, clinicians, we all have a role in that conversation, and we're obliged to take part in that conversation just as much as we're obliged to take part in the research. And we need to be part of the conversation that develops the appropriate regulatory framework, and also helps to implement that regulatory framework.
Can you hear? Sorry, we lost you for a second, or maybe I don't know whether the problem is from my side or your side,
Yeah,
but
you keep going off my screen. I don't know.
sorry. No, I get that. I mean, I understand. Just to summarize, you're saying that today, even the awareness of ethical issues is a lot more than ever before. So, I think also, Professor Wallace, there is a cross-cultural exposure. A lot of the scientists looking at behavioral science and a lot of the social scientists looking at science. There's a lot of cross-communication now than ever before, perhaps, and you flashed the different disciplines of people you have in your lab. In my time, it was, if you're an electrical engineer, that's how many were there in your discipline. If you were a mathematician, you only work with mathematicians. I mean, just in your lab, you're working with 6 different disciplines now, right? I think.
Yeah, lots, and it varies from project to project, and I think it was even worse than that. I mean, not only did you confine yourself to your own discipline, often you confine yourself to your own project within your discipline,
Right.
and that breadth of knowledge that's there at your fingertips, if you just engage with others, is so powerful. That engagement. There's no way knowing that we could tackle the Brain on the Bench project or any of those projects that I've mentioned, even within our own research group. And we've got lots of disciplines. All of those projects involve multiple groups around the country and indeed around the world.
Yeah. One more question is, a place like India has huge scale, right? We have like 1 billion people, 100 million people with a particular condition or whatever. There's a huge scale. So, as we look at new developments, new technologies, etc., where are the opportunities for countries like India who have the scale to leapfrog the legacy systems and get to new ways of being, by even skipping what someone had to do? I mean, for example, I say, okay, we don't have enough telephones, we just move to cellular phones, right? We don't have enough banks, we just move straight to digital banking. So, in the same way, in medical technology, what are some of the areas where India can contribute in a huge way to the forwarding of science?
Yeah, look, I think that's very much part of the project that we have with
Right,
AMTZ is
right.
learning how we
Right.
do that. So the prosthetics ear technology is relatively simple. We built a customized printer. We've done some nice approaches to the scanning technology and the software. So the real challenge there is, how do you deploy it? How do you deploy it? What's the most effective means of deployment of that technology in a country the size of India, and a country as big as India, and even a country as big as Australia? What's the most effective way to deploy new technologies? And if we answer those questions, then I think as newer technologies come along, we'll have a framework in place that will be very powerful. And that
Right.
knowledge and information is every bit as important as building the technology in a lab. How do you physically be and introduce innovative methods to ensure effective deployment?
It's interesting. This is what Alok is also asking. We've talked about Alok a little bit in terms of saying how better India and Australia R&D can, our joint collaboration can ensure faster translation into clinical bioprinting applications, because there is theory and then there is application, right? So because of the scale that we can offer, we would love to know your thoughts on how can we accelerate some of the clinical applications? What are some of the areas where we can do clinical applications?
Yeah, look, just about any of the clinical applications that we're working on, or others, could be deployed in India. I think our strategy at the moment is to, take the simplest technologies and build a deployment framework around that, and then to introduce the more complicated technologies as we go along. But there's no doubt that we're going to learn a lot through working, and we already have, through working with our colleagues in India, and a lot of it applicable in Australia, because Australia has a lot of remote areas where people can't get to clinics and can't access the latest technologies that are in Sydney or in Melbourne. So while we started this study from a non-technical point of view, focused on the India challenge. There's a lot of common things that, if we get it right, will be deployable and make sure we have more effective deployment here in Australia as well.
Right. The next question is from Shraddha, and while we addressed it a little bit, it'll be great if you can expand on this, is what can we do to accelerate the future of healthcare in the next 5 years to build effective interdisciplinary research and development teams? Like you just showed us in your center, how many universities you work with, right? How many, not just universities, entities you work with. So especially in India, since you're beginning to collaborate with AMTZ, etc., what are some of the things we can do even more of to have a more interdisciplinary research?
Yeah, look, this is sometimes not easy to achieve.
Right.
And I think the only way to really achieve it and accelerate it is to demonstrate to people the advantage of doing it. And I think that's what's happening at AMTZ, and that's what's starting to happen for us as well. So I think for a long time, and it's true here in Australia as well. I mean, not everybody collaborates very effectively. For a long time, people were told to collaborate, that collaboration was a good thing and you should do it. But that approach doesn't really work. I mean, I think what works is people seeing, because most researchers are passionate about delivering something out of their research that will benefit their community. And if they can see examples coming forward, as we're seeing, and we have over decades now, but we're seeing more of them, as we see those examples, and that they were only possible through collaboration. I think people get inspired to collaborate because they want to do that. They want to achieve that. The most amazing story of collaboration that I know is Professor Graham Clark, when he developed the bionic ear more than 50 years ago or 40 years ago. Now, that was back in a conservative time in conservative universities. And you can imagine the number of different skills that Graham had to bring together in order to develop the bionic ear. And his book that describes that, it's an amazing feat of driving for collaboration. And why did they collaborate? Well, if you ask Graham, and the team had to stick together for a long time because they wanted to have the bionic ear. They wanted to help deaf people to hear. That was the driver. That's what brought them together. That's what kept them together. And I think it's big visions like that and big drives like that that build collaborative teams and keep them together.
The next question is from Siddharth. He's asking, what are your thoughts on the applications of bioprinting in space or space travel?
Yeah, it's interesting. We've been asked that question a number of times, and I thought, look, it's something that we have to look at. There's no doubt. I mean, we're talking about remote places in India and Australia before, but there's nothing much more remote than out in space. And if you need a spare body part or something that can help repair, yeah, 3D bioprinting will have to be something that's utilized in space, I think.
Yeah, and I think actually there was a startup some time ago in Silicon Valley. They were testing first of all how will a printer, work in that atmosphere. First of all, just technically, mechanically, how will it work in that atmosphere? And then to say, can I print? As you were saying, like my spaceship, blah, that valve is gone. It's not like you can write and get it by mail, right? So you have to print it yourself. So
Yeah. I mean, I think it's an area where 3D printing will have a big impact, and as the different aspects of 3D printing are developed, they'll just be incorporated into space travel for sure.
And we never know, maybe we can 3D print our food as well. I mean, because right now the people take the most insipid food to survive for years, right? Just dry food, etc. So
yeah, I know there's a colleague here, I think he's at Queensland University of Technology, who's looking at 3D printed food, and
yeah,
that's another fascinating area. And he's not even talking about 3D printing meat, for example, from cells and combinations of cells, but just different food ingredients
correct.
arranged
Yeah.
in 3D structures that give you good nutrition but good taste as well.
Yeah. So far we've taken questions that came online. I would love to, we have audience in AMTZ there, and I'm sure there are mics. So we would love to open it up for questions from the audience in the auditorium. Does anyone have any questions? And to share, maybe if there is a way in which you can get them to ask the questions, please feel free, because we'd love to have you participate. Okay, while you guys are thinking, maybe I'll ask you a very personal question, Dr. Wallace, is that in science, especially in science, you don't know when the results are going to come for what you're working. And sometimes it may be 2 other generations that will build on what you have done and make it successful. So at the same time, you have to maintain the rigor to work as though it's going to be released tomorrow. I mean, you have to have the same enthusiasm. So personally, is there a story or is there something you have seen happen where you felt, my God, if that little thing happens, it's worth dedicating my life to do this? From a scientific mind, how do you keep yourself motivated? What motivates you? Is there a story from your background? Is there something that you say, wow, I saw that and that's what inspires me to do this?
Look, I've always had an interest in the development of new technologies and their use in medicine, but I sort of fell into it. I didn't plan to get into it, but the opportunities just kept appearing in front of me as we went along. And as I sort of tried to convey in the story of the brain on the bench, I mean, it's incredible opportunities that have been put in front of us in the era we live in today. I do get jealous of younger people who are just starting their career now, because as I say to them, I think they'll achieve more in the next 5 years than we did in the last 25 years.
Correct.
Because
And you have
because
achieved
of that
something that your
convergence,
predecessors achieved in 50 years or 100 years, I mean.
yeah, and it's because of that convergence and that total change in culture, as we mentioned. The culture has changed totally. These people are being trained in a culture of collaboration. That they're learning to think about ethical and regulatory and commercial issues. Not that they have to drive them, but they have to understand them and understand that they could be the roadblocks to implementation. And I think what keeps you going every day, I mean, we all know that research can be disappointing. It can be disappointing sometimes, but in between those disappointments, there's a lot of, even if there's small wins, I didn't mention one project today. We're working on a corneal regeneration project with a surgeon in Sydney. And along that journey, that's a complicated project, but along the journey, the surgeon said to us, well, this first ink that we've got, let's just try it to see if it can heal just small wounds in the eye. and even maybe little deeper wounds. And we tried that, and it was successful. And this surgeon works in Myanmar as well, where 50% of the cases of blindness come from those very small wounds. So what an exciting application that's of immediate benefit to people while we pursue that longer term goal of complete corneal regeneration. Those stories that happen to us every month just keep you bubbling, I think.
Sure, absolutely. Go ahead, from AMTZ, please tell your name and then say your question, please.
Lakshmi, I am Mohini from AMTZ.
Okay.
Hello, Mohini.
Hello, Professor. I have taken up his course on the short course on 3D.
Okay.
Having this conversation with my colleagues, the generic question is something on what you said a little while back. 3D bioprinting is generally considered as something which is very patient specific. And when we see a country like India, where we have problems in the masses, how do you see 3D bioprinting as a solution to those kind of diseases? Is there a future for that, or is it going to be something that's going to be patient specific through and through?
Great
Well,
question.
I think there's two things to that, Andy. One is that patient specific can still be deployed en masse. You're talking about patient specific things, but patient specific things that are simple to deploy. So I think for some things you can still have en masse distribution of patient specific solutions. But having said that, there will be other areas where 3D printing is used to just generate things that are not necessarily patient specific. So a very simple example of that is the prosthetic ears. Our challenge there, or our plan there, is to get the scan of the ear that's missing, to build quite a common framework, but the prostheticist would finish those individual ears for particular patients, and that still cuts a lot out of the workflow, the traditional workflow for prostheticists. So yeah, there will be different technologies that will do en masse production, but I still believe there will be situations where customized solutions can be delivered en masse as well.
Thanks. Good evening. I'm Dr. Kavita. I want to ask one thing. Are there any risks associated with this 3D printing?
Risks?
Yes.
Yes. There's risks associated with any new technology, and I think that's why it's important, as Lakshmi said before, that we as researchers have an obligation to make sure that those potential risks are identified and minimized as part of the research process. So it's not up to anyone else to do that. It's not their responsibility. It's the responsibility of researchers to engage in those conversations and make sure that we are minimizing risk as well. Otherwise, the technologies will not be deployed. So we have to accept that there are potential risks, as there are with any new technologies. And of course, that's heightened when it's a medical technology, and be responsible in identifying and minimizing them.
Sorry. Also, Dr. Wallace, we are probably quite a few years away from learning if there is, first of all, we don't have 3D printed organs yet. If we have the 3D printed organs and put it in human beings, what is going to be the acceptance and how long can it last? There is probably a whole bunch of studies that need to be done for us to get to a point to say, this is the reality,
Yes.
I mean, so I think there's a ton of work to be done, especially in clinical trials, and for probably years before we know what works and what doesn't work.
I totally agree. So where we can have the biggest impact at the moment is in using 3D printing to facilitate the natural regeneration of damaged organs, or to facilitate the performance of implanted structures, for example. And of course, in doing that, we're learning a lot about what we need to do to create those 3D printed organs.
Correct.
And also in planning for that, though, I think it's important again that right at the start we're engaged in conversation with people about, let's pick materials that are going to be easier to regulate, for example. Let's pick technologies that maybe have a prior history as implants that we can modify with 3D printing in order to accelerate adaptation as well. We need to be very careful in the planning stages, and that's why that statement, which was probably a little bit glib, don't wait until the end, until starting to translate. You really need to be in those conversations early. We all need to be in those conversations now about, even though we know it's some years away, about 3D printed organs, let's set up the framework so that we can maximize the chance of success technologically, but also from a regulatory point of view, from a scale-up point of view, a commercial point of view, and an ethical point of view. Let's have all the conversations along the journey.
Correct. So I'll take the last question. This is from Dilip Kumar Chekuri. Says, interesting research work in India. Is looking forward to your collaboration with AMTZ, of course. He wants you to explain a little bit more about graphene and cartilage regeneration material.
Yeah. So they're two separate projects, but it was interesting that the cartilage idea initially spun off. Let me go back. So we wanted to 3D print graphene to make structures for neural interfacing. We introduced a biomaterial to that to give us printability. That biomaterial was chitosan. In a casual conversation with the orthopedic surgeon, he said, chitosan's been used for cartilage regeneration previously with adipose stem cells, but it didn't work very well. But what about if we could 3D print an arranged structure that with very careful distribution of those stem cells, maybe it would work. And again, so you can't imagine a simpler 3D printing project, but it was the combination of that knowledge from the stem cell area and the clinical area, identifying that need for the 3D printed component to make it work. So there's no connection there between chitosan and the cartilage and graphene, other than a conversation that we had and a surgeon's awareness that, hey, I could use that. And it's turned out that we have used the chitosan graphene now for bone regeneration as well.
That's great. Professor Wallace, before we wrap up, I'd like for Rohan to play a video on Indian Biomedical Skill Council. So Rohan, why don't you play that, and then we'll come back and wrap up.
Good morning and welcome to a presentation on Indian Biomedical Skill Consortium. Indian Biomedical Skill Consortium is a professional body constituted by the NABCB, the National Accreditation Board for Certification Bodies, the IMED, Indian Manufacturing Association of Medical Devices Manufacturers, and AMTZ, the first and only medical devices manufacturing ecosystem in India. These three large entities pertaining to their work in medical devices got together to set up the Indian Biomedical Skill Consortium. The IBSC proposed for job roles in accordance with the National Qualification Register under the National Skill Development Agency. This was approved, and IBSC now offers 5 NSDA-approved job roles for biomedical engineering for those engineers working in the field of medical devices, equipment, and life-saving machinery and working in manufacturing units, R&D laboratories, hospitals, installation bases, and so on. The IBSc job roles are spread across various technological and academic modules, which range right from understanding of medical electronics to radiation safety. The 28 modules spread across 5 job roles provides for competent assessment of a person's experience and expertise based on educational qualifications and their understanding of the knowledge domains. IBSc is also fortunate to partner with large number of international partners such as AMI, the US, and so on, so that our modules are internationally harmonized and synchronized to the global requirements. It is also very unique that Indian Biomedical Skill Consortium does not charge for any fee for accreditation under the job roles until the applicant has passed the modules pertaining to a job role. Therefore, a candidate gets the privilege to apply for free, undertake the assessment, qualify, and after they qualify, they pay a nominal fee for the respective job roles. The NSD approved qualification certificate which is issued to them also comes with large number of training opportunities and training programs that AMTZ and its partners conducts for the stakeholders. The Indian Biomedical Skill Consortium is now having a partner base of more than 50 credible institutional partners, right from institutions like IITs, private consultancy firms, and institutions with deep knowledge base in medical technology. I welcome all of you to the IBSc family and hope that your involvement with IBSc would nurture your knowledge and your credibility of expertise and experience in a phenomenal way. The IBSc certificate would carry the hallmark, the QR code of the candidate, which allows seamless recognition of the certification and the skills carried by an individual. Welcome to the IBSc family once again, and hope that IBSc supports you in true expression of your skills and knowledge. Thank you and Jai Hind.
Great. Thank you very much for that. Sorry, is there some echo from my side? Anyway, we'll try to wrap this up. I just want to thank by saying, first of all, I really want to acknowledge Dr. Jitendra Sharma, AMTZ, and Dr. Sharma's unstoppable energy. I think none of us would be here but for that. So I really want to thank him and his team, Shishir and Dr. Kavita, all of you who have really made this a great success. And secondly, I would love to thank our team at Inc., Vipasha, Rohan, and everyone who's been working on this. And finally, the most important thing, Dr. Wallace, thank you. And also your amazing team at the Wollongong University and all the partners that you have collected to do something absolutely world-class. And this collaboration is fantastic, and we look forward to getting to know you more and also know more of the research. And best of luck for everybody. And thank you so much for everyone who joined us on the stream as well as in live to explore new frontiers of science in the area of 3D printing and the impact it can have on overall social good. With parting words, Dr. Wallace, are yours, and we are ready to wrap.
Okay, well, look, thank you again for the opportunity to join with you in this really interesting event this evening. It's always great for us to share our most recent findings with our collaborators around the world, and I think that there's no doubt that as we continue to work together, we'll achieve amazing things that will deliver significant solutions to some big medical problems in the years to come. So let's keep working together and dare to dream and be determined to deliver.
Great. Thank you so much. And the entire AMTZ